Welcome back everyone to the second video lecture on flexible bodies. In the last lecture, we discussed regarding the three CMS methods supported in OptiStruct. They are the Craig-Bampton method, the Craig-Chang method, and the Craig-Bampton geometric stiffness method. I hope everyone is clear with these three different CMS methods used for generating the flexible bodies. However, just knowing the three different methods will not be of any use without knowing their practical applications or when we are supposed to use a particular type of the CMS method. So in this slide, let's discuss regarding the selection of CMS methods for different applications. It is highly recommended to use the Craig-Bampton method when most of the degrees of freedom of the interface nodes are constrained by the MBD model. The Craig-Chang method can be used when most of the degrees of freedom of the interface nodes are not constrained in many degrees of freedom by the MBD model. In other words, this method is very effective when the interface nodes are free. The Craig-Bampton geometric stiffness method is supposed to be used when you are analyzing slender structures that have large influence of geometric stiffening effects, especially during spinning, such as in a case of helicopter blades or ceiling fans, etc. Moving on to the next slide. I believe all those having a background in FEA understand the meaning of normal modes analysis. For those of you who don't know what it means, here's the explanation. A normal mode is a motion where all parts of the system are moving sinusoidally with the same frequency and in phase. All observed configurations of a system may be generated from its normal modes. Each normal mode has a characteristic frequency, that is, its eigenvalue. The Craig-Bampton and the Craig-Chang modes are not the same modes as calculated using the conventional normal mode analysis. They may look really similar, but strictly speaking will not compare exactly with the normal modes analysis. So if you compare the modes generated by Craig-Bampton and Craig-Chang methods, it won't be the same when compared to the normal modes analysis. Now let's see how we can calculate the number of modes generated to represent a flexible body. It is equal to the number of degrees of freedom restricted for each interface node, which are nothing but the static modes, in addition to the number of fixed interface or the free eigenmodes that are requested by the user. Let us consider an example to make things more clear. If a flexible body has 4 interface nodes and the user requests 10 free eigenmodes, the number of modes generated to represent a flexible body will be equal to the 4 interface nodes multiplied by the 6 modes per node, which makes it 24, plus the 10 free eigenmodes requested by the user, which will give you 34 modes in total. Another important requirement in the CMS method is that the exterior grid points must be able to move independently of the interior nodes of the flexible body. A common case that causes CMS failures resulting in an error during flex body creation is when the center point of the rigid spider, which is defined as a flexible body interface node, is dependent on the displacements of the outer nodes, which is nothing but a RBE3 element in OptiStruct. This is shown in the figure on the right hand side of the slide, where the node ID 4887 is represented by letter D, and this is the node of a RBE3 element. The user can change the configuration of the RBE3 element to a RBE2 element with an independent center node in HyperMesh. This will be illustrated in the exercise demo in the next video. We will interactively use the FlexPrep utility to invoke HyperMesh during the creation of the flexible body to change the RBE3 spider into RBE2 spider. Okay, now let's move on to the next topic, that is Eigenvalue Solver. This topic is covered in this chapter only to introduce you to the two different algorithms used in OptiStruct to perform normal modes analysis. They are the Langour method and the automated multi-level substructuring eigenvalue solution, also called as the AMSYS method. The eigenvalue data extraction for Langour is specified on the EIGRL data cards, and for AMSYS It is specified using EIGRA data cards. Now I will give you a brief explanation on both these methods. Langour's method. The Langour's method has the advantage that the eigenvalues and the associated mode shapes are calculated exactly. This method is efficient for calculations in which the number of modes is small and the full shape of each mode is required. The disadvantage of the Langour's method is that it is very slow for large problems with millions of degrees of freedom, for which hundreds of modes are required. The run times for these types of problems can easily stretch into days. Now, let's concentrate on the pros and cons of the AMSIS method. The AMSIS method has the advantage that only a portion of the eigenvector needs to be calculated. Since only a portion of the eigenvector is calculated, the disk space is greatly reduced. This leads to much shorter run times. For a typical multibody dynamics system's frequency response analysis, there's only about 100 degrees of freedom of interest. The major disadvantage of the AMSIS method is that the calculations are not exact. However, the modal frequencies are still accurate to a few digits. But by default, the solver algorithm is set to Langour's method. Now, let's concentrate on the flexible file or the flexible body generation using the FlexPrep utility in Motionview, which basically runs OptiStruct in the background. So the user can generate flex bodies in Motionview in the following ways. We can either use the FlexPrep utility in Motionview interface to create the flexible bodies, or we can use HyperMesh to set up the model and run it in OptiStruct. The third way is for the advanced users to manually edit the FE input file before solving it in OptiStruct. In this method, we can include cards to reduce the size of the flexible body. However, in this chapter, we will build our flexible body using the FlexPrep utility tool. Once the FE solver creates the flex body in the H3D file format, it is imported to MBD model and connected to MBD model constraints, motion, forces, etc. Finally, the MBD model with the flexible body is simulated using Motionsolve, Adams, or other compatible multibody dynamics systems solver. Please note that Adams simulations require a file conversion from .h3d or .mnf. In this slide, I will explain the FlexPrep utility used in Motionview interface. It is found in the Tools menu. You need to click on the Flex Tools options in the toolbar and then click on the FlexPrep option to invoke the utility. I have pasted a screenshot from the Motionview GUI in this particular slide. I'll be switching now to the software to explain the dialog box in detail. So this is the Motionview GUI. Here you can find the Flex Tools in the menu bar, and then when you click on the Flex Tools, you need to click on the first option, which is called the FlexPrep, to invoke the FlexPrep utility dialog box. The first radio button is OptiStruct Flex Body Generation. So this radio button has three options in the drop-down menu. The first option is to create OptiStruct preparation file and also generate the Flex Body H3D file. The second option just creates the OptiStruct preparation file. And the third option, it creates the FlexBody H3D file using a pre-existing preparation file. The second radio button basically is used for translating the FlexBody files from one format to another. It has 5 options in the drop-down menu. In that, the first option is to translate the Adams MNF file into H3D file format. The second option is used for mirroring existing H3D flexible body across a particular plane. So we will be using this particular option in our exercise demo to mirror the left lower control arm to the right lower control arm. The third option is to translate the H3D file format into Adams MNF file format. The fourth option is to translate the H3D file format into Adams MTX file format. And the last option here is to translate the H3D file format into DADS file format. The third blank that you can see here is to import the FE model that you want to convert into the flexible body. So you can click on this folder icon here and you can select your required FE model that you want to convert into the flexible body. The fourth option here is your flexible body location. So you can give the location to store your flexible body and also the file name for your flexible body. And it will have a .h3d extension. The fifth option allows you to select the CMS method that you want to use. I have already covered the topic on how to choose the CMS methods earlier. So depending on the applications, we can select the CMS method. So you have the three CMS methods here, the Craig-Bampton, the Craig-Chang, and the Craig-Bampton geometric stiffness methods. And by default, it is the Craig-Bampton method. In the next option, you can specify the interface nodes. Please make sure that you separate the interface nodes with a plus sign, as shown in the syntax here. So for example, let me give you an illustration. So if your interface nodes are 98, 9898 and 9899, then you need to separate them using this plus sign. In the next option, you can specify the frequency cutoff type and its value. It is nothing but the user specified value for the number of modes of the flexible body. Here, you can specify the Eigenvalue solver mode. And as I mentioned earlier, it is always defaulted to the Langour's method for creating the flexible bodies, and it cannot be changed. On the right hand side of the dialog box, you can see the Create RBE2 Spiders option. If you click this particular option, it will invoke HyperMesh on the fly and allow you to convert all the RBE3 spiders connecting the interface nodes into RBE2 spiders. If you do not have these RBE3 spiders, then you really don't have to worry. But if you have these RBE3 spiders, then you should make sure that all the RBE3 spiders, which are the interface nodes in your flexible body, will be converted to the RBE2 spiders. Otherwise, you will be ending up with an error. Now, you can see this additional options tab on the dialog box. If you click this, it brings up this particular dialog box, wherein you need to check the perform stress recovery and the perform strain recovery options in order to get the stress and strain results. And the rest of the options in the dialog box you can leave as default. Now let's go back to our presentation. So now let's talk about the units. A consistent set of units is defined as, for example, one force unit is one mass unit into one acceleration unit. One acceleration unit is equal to one length unit divided by one time unit square. One density unit is basically one mass unit divided by one length unit cube. Fortunately, when creating a flexible body .h3d file for Motionview, the values entered in the fields are not required to form a consistent set of units. For instance, the mass unit can be in kg while the length unit is in millimeters. OptiStruct manages the units for the flexible body output through the DTI unit cards. For units to be consistent between the flex body and the MDL model by which the flex body is utilized, the units of the FEA model must be identified. This unit information is stored in the .h3d file, and all the affected parameters in the solver flex body matrix file are scaled accordingly. Now let's discuss about the quasi-static analysis and its solver settings. We will understand the following in this particular slide. The first thing is the definition of the quasi-static simulation or the quasi-static analysis, and then the solution overview. So definition. So physically, quasi-static means almost static, which means that the system is being driven extremely slowly so as to not engage any transient dynamics into the simulation results. Mathematically, quasi-static simulation is a sequence of static simulations performed over a given duration. It is useful when the model contains time-dependent forces or motions and the user is interested in the sequence of equilibrium configurations the model passes through for a given period of time. And this is the solution overview. The forces or motions are a function of time. Velocities, accelerations, and any time derivatives are set to 0. The generalized coordinates and constraint forces are the unknowns. Motionsolve calculates the static force balance problem at every time step. Governing equations are algebraic in nature and solved with Newton-Raphson method. So, we'll be creating and simulating the flexible lower control arm in our exercise demo. As you can see, we can get the suspension system which is already there in Motionview library, and then after importing the suspension system which has the rigid lower control arm, we'll be replacing it with the flexible lower control arm both on the left hand side as well as on the right hand side. And then when we perform the analysis and run the animation, we can see the stress and strain distribution on the lower control arms. So the steps that we'll be following to do this particular simulation are: in step 1, we'll be using the FlexPrep utility tool to generate a flexible body. Next, we'll be creating the RBE2 spiders, meaning there are RBE3 spiders in the FE model. So we'll be going to HyperMesh and we'll be converting the RBE3 spiders to RBE2 spiders to make the center node independent. In step 3, we'll be ensuring that the interface nodes are independent. In the next step, we return to the FlexPrep utility and run OptiStruct. In step 5, we'll view the model and verify the results. In step 6, we'll be using the FlexPrep utility to mirror a flexible body. So here, we'll be mirroring the left lower control arm to get the right lower control arm. In step 7, we'll be replacing the rigid bodies with the flex bodies and solving it in Motionsolve. And in step 8, we'll be viewing Motionsolve flexible body results in HyperView. So I'll be doing the exercise demo in the next video. Thank you.